Welcome to the Explainer. So you're in a calculus course, and you've probably hit those functions that are just a nightmare. The ones that are impossible to integrate or a total mess to differentiate. But what if you could rewrite them as something you already know really well, like a polynomial? Well, that's pretty much the magic of power series. They're one of the most powerful tools in all of higher math, and today we're going to break down what they are and, most importantly, how to figure out where they actually work. So here's our game plan. We'll start with the basics, what a power series even is. Then we'll tackle the big question of convergence. After that, I'll walk you through the step-by-step method for finding the interval where these things are valid, give you a pro tip so you don't make the most common mistakes, and then we'll put it all together with a couple of solid examples. All right, first things first, what in the world is a power series? The easiest way to think about it is just as a polynomial that never ends. It just keeps on going. It's an infinite sum of terms that we can use to build, or at least approximate, other functions that are way more complicated. Okay, let's look at the formula. Don't let it scare you. See those Cn terms? Those are just numbers, coefficients, that give each piece its weight. And the x min a part? That's the real engine of the series. It tells us the series is centered around some number a, and each new term just adds a higher and higher power of x min a. This is our fundamental building block right here. And that leads us to the single most important question. A regular old polynomial works for any x you can dream up, but an infinite one, that's a whole different story. If you plug in some values for x, the sum might settle on a nice finite number. But for other values, it might just explode and shoot off to infinity. We need to find its safe zone, the range where it actually behaves like a proper function. So this brings us to the core concept of convergence. Finding where a series converges is just the fancy math way of asking, okay, for which x values does this crazy infinite sum actually add up to a real finite number? And the good news? There are only 3 possible outcomes. It's pretty straightforward. First, the series could be kind of boring and only work at its dead center, x equals a. Second, it could be incredibly powerful and work for every single number on the number line. Or, and this is the most common case, it works within a certain distance, a radius from its center. So, how do we find that safe zone, that interval of convergence? Well, luckily for us, there's a fantastic, reliable method. Let's walk through the 3-step process that you can use on pretty much any power series problem they throw at you. This right here, this is our recipe. Step 1, we use a tool called the ratio test. It's perfect for this. Step 2, we take the result from that test, this limit L, and we force it to be less than 1. That'll give us our main interval. And then step 3, and listen up because this is absolutely critical, we have to go back and check the 2 endpoints of that interval all by themselves. Let's really zero in on that 3rd step. Seriously, I'm calling this the pro tip because forgetting to check the endpoints is, hands down, the #1 mistake students make. The ratio test is great, but it has a blind spot. It fails right at the boundaries of the interval, so you have to deal with them separately. Think of it like this. The ratio test gives you everything inside the interval. It tells you with total certainty what happens between a minus r and a plus r. But at the exact points, x equals a minus r and x equals a plus r, it tells you absolutely nothing. It's a total gray area. They could converge, they could diverge, we just don't know without checking. So the takeaway is simple. You cannot skip this step. You have to take each endpoint value one at a time, plug it back into the original series, and then use one of your other tests, like the p-series test or the alternating series test, to figure out what happens. All right, enough theory. The best way to really get this down is to see it in action. So let's get our hands dirty and walk through a couple of classic examples that really show you the whole process from start to finish. Okay, here's our first problem. Looks pretty standard. We've got a series centered at x equals 2 and a few different pieces floating around. Our mission is to use our 3-step method to find the complete, total interval of convergence. All right, let's do it. Step 1, we hit it with the ratio test. After you set it all up and all the dust settles from canceling terms, the limit L simplifies down beautifully to the absolute value of x minus 2 all over 4. Now for step 2, we apply the condition for convergence. We set that whole thing to be less than 1. When you solve that inequality, all x minus 2 less than 4, it tells you 2 things at once. The radius is 4, and our starting interval is from -2 to 6. And now for the moment of truth, step 3. This is exactly why it's so important. We test the left endpoint, x equals -2.
When we plug that in, the series turns into the good old harmonic series, which every calculus student knows diverges. Then we test the right endpoint, x equals 6. That one turns into the alternating harmonic series, which converges. See? The two endpoints do completely different things.
So, putting it all together for our final answer. Because -2 diverged, we use a soft parentheses there. But because 6 converged, we use a hard square bracket. So the complete final answer for the interval of convergence is -2, 6. Let's do one more. This one looks way simpler on the surface, but that n factorial on the bottom, oh, that changes everything. This is a super important series, by the way. It's actually how you build the function e to the x. Okay, we fire up the ratio test again. After we simplify everything, we're left with the limit of the absolute value of x divided by n plus 1. Now, just think about what happens as n gets huge. It doesn't matter what x is. That denominator is racing off to infinity. The bottom of the fraction gets so enormous that it just crushes the x on top. The whole thing gets pulled down to 0. So our limit, L, is just 0. Now we check the condition. Is L less than 1? Well, yeah. 0 is always less than 1. It's true no matter what value you picked for x. The condition for convergence is always met. And there you have it. This is the second of those 3 big possibilities we talked about. This series converges for every single real number. Its radius of convergence is infinite, and the interval is the entire number line. That n factorial in the denominator is just an absolute powerhouse. It tames the xn term, no matter how big x gets. So at the end of the day, finding the interval of convergence is all about mapping out the safe zone for these incredibly useful new functions. Once you master the skill, you've unlocked the ability to represent some of the most important functions in all of science, like e to the x, sine of x, and cosine of x, as infinite polynomials. And that is the foundation for so much in engineering and applied math, which really makes you wonder, what other secrets are just waiting to be found inside an infinite series?